Why is there a gap between the specified compressive strength used in calculations and the average strength used for concrete mix design? In this tutorial, I'll share with you what I learned from James Wight's and Darwin and Dolan's books. Before we dive into the philosophy of average compressive strength, let's talk about the definition of a specified compressive strength, or F'(C). As I explained in this video, F'(C) is the average strength of at least two 6 by 12 inch or 4 by 8 inch cylinders from the same concrete batch tested at 28 days. Due to the inherent variability in materials testing and construction, we must incorporate a safety factor beyond our required design strength. Our ultimate goal is to achieve a very low chance that the actual provided concrete strength falls below the F'(C). Let me start with a real-world truth. Similar to most natural phenomena, the concrete strength follows a normal distribution. This means that if we aim for 4,000 psi compressive strength, it is possible that 50% of our test results fall below that target statically. It is too clear that it is completely unacceptable for structural safety. The variance, or how precise these measurements are, is quantified by a standard deviation, typically denoted as S. A larger standard deviation indicates more variability or a wider distribution of strength results. This means that the actual strength results are more spread out from the average. Conversely, a lower S signifies greater precision and less variability, meaning strength results are clustered more tightly around the average. Due to this unavoidable variation, we have to design for a higher strength than what the structure nominally needs. This brings us to a new definition, the required average compressive strength, or F'(CR). As I said before, the F'(C) is something for engineers to use in structural calculations, while the F'(C) is what actually aimed for our concrete mix design, and it is definitely higher than F'(C). We tackle this with a specific goal: only a 1% chance that the final concrete strength falls below our specified compressive strength. To achieve this low probability, we effectively increase our concrete mix design target. A larger S means less reliable concrete production, and finally, a bigger gap is required between F'(C) and F'(CR). Poor quality control literally costs money because you need to over-design. This translates to lower water to cement ratios, higher cement, and even more admixtures. ACI 214 provides specific equations to calculate the target strength based on the amount of test data available for a particular concrete mixture. ACI knows that not every project has the same level of concrete testing data, so it provides three different approaches based on our available data. First of all, if we have at least 30 test results, we can determine S with a reasonable approximation. Then, to define F'(C), we use one of two sets equations based on our F'(C) in this table. Remember that any test result is the average value of at least two cylinders. This gives us the most precise calculation of our F'(C) using statistical equations that account for our specific production variability. In the second scenario, we have fewer than 30 tests, so the standard deviation estimation is less accurate. In this case, we must multiply the calculated standard deviation by an added modification factor. This modification factor increases as the number of tests decreases. For example, with 25 tests, it is 1.03, and with 15 tests, it jumps to 1.16. We should interpolate for values in between in this table. After modifying the standard deviation, we applied the same target strength equation as for 30 or more results. This conservative adjustment ensures we don't underestimate the required safety margin. Finally, if we lack enough prior testing information, ACI provides simpler and more conservative equations. These do not rely on a calculated standard deviation. They give us a safe starting point but tend to be more conservative than the statistical approach. You can see different equations to calculate f prime c for different values of f prime c in both SI and USC unit systems in these tables in this scenario. To save your time, I have brought a complete example from Darwin and Donner's book here. If you want to know how to use these equations in practice, I invite you to pause the video and read it yourself. So here's what you need to remember. F prime C is what your structure needs. F prime CR is what you specify to account for variability. Better quality control means lower standard deviation. This leads to smaller safety margins and lower costs. If you found this tutorial helpful, please hit that like button and subscribe for more. Thanks for watching, and I'll see you in the next one.